Moving on to bending due to eccentric axial load. So when we have a loading condition in a bending member as such shown in figure 15, there is an internal moment created while there is also an axial force acting on the cross section. Okay, that means that we have combined stresses at this point. Bending stresses are created because of the eccentricity of the load, meaning that it does not pass through the centroid of the cross section, and also since there is an axial load or an internal axial load that is supposed to resist the applied load, there is also axial stress. Okay, so your normal stress diagram, when you analyze the cross section, will look something like this. There is a uniform stress due to due to the axial force, and then plus a stress caused by the bending moment. Okay, so it can be thought of this plus this, and so it could happen that your your stress here could be smaller because of the presence of the axial force when this is in tension and your bending stress is in compression. Also, your tensile stress at this point can be multiplied rather with the presence of an additional uniform stress. Okay. Also, it can also happen that this is all in tension, all in compression, and whatnot. Okay, so you have to be vigilant in what you're calculating. All right, so that is why here we have whenever an internal force F acts simultaneously with an internal bending moment, the neutral axis is no longer located at the centroid of the cross section. Okay, it's not always the fact that it's not located at the centroid. Okay, in fact, depending on the magnitude of the internal axial force, there may be no neutral axis at all. All normal stresses on the cross section may be either tension or compression. Okay, and to get the stress, okay, let's say at this point, at the topmost point, it's just this stress here plus this stress here, and that's why we have this equation here, Fa minus My over Iz. Okay, now M can be expressed in terms of the force times the eccentricity, or the moment arm of the force, okay, or of the applied axial load. And that is P times E. Okay, that's why we have F over A minus PE Y over Iz, where PE is just equal to M. Okay, so let's go over example M8.4. The C-clamp shown is made of an alloy that has a yield strength of 324 megapascal in either tension or compression. Determine the allowable clamping force, okay, P, shown here. The clamp can exert if a factor of safety of 3.0 is required. So there is an element that is foreign to you here. It's the factor of safety. Okay, so we'll be going over that. After determining the moment in the not really the moment yet, the section properties of the beam, okay, of the cross-sectional area of the C-clamp. Okay, so from here we have to determine the location of the centroid by use of Varignon's theorem. So we already know how to go about this, and we will see that the centroid is 10 inches from the reference axis, which is the bottom axis. Okay, now by the parallel axis theorem, we will see that the moment of inertia is equal to 2176 mm to the 4. All right. Actually, this is not supposed to be inches. It's supposed to be in mm. Okay, in millimeter. So be careful of your units again, especially if you're taking your exam. Okay, so since there is a factor of safety, the yield strength has to be divided by the factor of safety to determine the allowable normal stress of the material. So the point of a factor of safety is to give us an allowance of how many megapascal, so as to over design the C clamp so that it can withstand any unforeseen loading. Okay, this is a concept very useful when it comes to your structural design. Okay, so moving on, we will then determine the internal axial force and the bending moment in the clamp. So we know the bending moment is basically just the distance from the centroid of the cross section to the point of application of the force, and that is 40 plus 40 plus 6, and therefore our moment is P times 46 mm. Also, by summing up forces in the X, we know that F, or the internal axial force, is just equal to P. Alright, so I hope that's clear. Next, we can determine the individual stresses by axial and then bending, okay? Because we are looking for the bending, the allowable clamping force. So we have 2 points here where your maximum compressive and tensile stress will occur. That is at the outermost fiber of the cross section, and that is denoted here as point H and point K. All right, so we will be determining the axial stress first. That's easy. That's P over A, and we already know A. So since we have to determine P, we will just leave that as a variable. Now for the bending stress of H, we have My over I. We already have I. We already have M. No, we don't really have M yet. We have M, which is P times 46. Y is 6 mm because that is the distance from the centroid towards the outermost fiber where H resides. Okay, and so goes for K. Okay, so we have 6 and 10 here. All right, now to determine the allowable load P from the combined stresses due to axial load, you have to visualize your stresses. Okay, so we have an axial stress here, which is a uniformly distributed load, and then, or a uniform stress, and then we have the bending stress, which is linear in fashion. Okay, so the combined stress is just the axial stress plus the bending stress at that point. All right, so in effect, for point H, based on the stress diagram here, your combined stress for point H is the axial plus the bending. Okay, now we know that we have an allowable bending stress, which is 108 MPa, which is Newton per millimeter squared. Okay, for either compression or tension, right? So that is what we will be placing in here. Now this is essentially an equation in terms of P. So we can solve for P using this equation right here. So P based on point H is just basically 787 Newtons. So that's the allowable clamping force that we can exert on the clamp. Now we have to determine also point K, because point K is on the opposite side of the cross-sectional area. Okay, so we have, this is supposed to be negative, by the way, negative 10, because it's located below. Again, it's located below the Z, the neutral axis rather. Okay, so that's negative. Okay, so from the stress diagram, we have the combination. This is supposed to be K as well. Okay, the combined stress is just equal to the axial plus the bending. Okay, and since it's negative, okay, this is, you can take away the negative. You can already take away the negative here because the negative sign is already incorporated into this part here. Okay, into this subtraction sign. Okay, so you will be able to solve for 530 for P of 537 newtons. Now the allowable load is 537 because it is the smallest load. Now if you load 787, your point K will fail. Okay, the stress at point K will be too great so as to so as to cause failure. Okay, point K can only accommodate a P up to 537 newtons, and therefore we will always be, when designing, we will always be mindful of the minimum value so that we can design it to be safe. Okay, so therefore we have determined the allowable load P, which is 537 newtons.